Hi everyone, I'm Weizmann Kiendrébéogo. I'm a postdoc at the CA working on Astro-COLIBRI, but today I will talk about our optimal follow-up using Ultrasat with M4OP. So M4OP is our framework that we use to generate observation plan. So typically similar to TALPI, but we have a different implementation and different optimization. Okay, but why do we need to prepare observation plan? To answer this question, let's first define what a kilonova is and why these matter. A kilonova is the light produced when two neutron stars or a neutron star and black hole merge. This light come from the radioactive decay of the heavy element. Typically, we have the gold or the platinum. And the kilonova can emit across UV, ultraviolet, the optical, or infrared. We have two types of kilonova, the blue kilonova and the red kilonova. The blue one comes from the low opacity ejecta, and the red one come from the high opacity. Okay, the GW1708-17 event show a very bright blue light, but unfortunately, it's about 15 hours after the gravitational wave detection that Swift satellite detected the first UV. Then, and when we realize a simulation, okay, maybe let's say first that this blue light may come from the air process that we identify here, like the nucleosynthesis and the shock made by the jet. So a simulation of both models using the context of UVEX give us this figure. UVEX is the Ultraviolet Explorer, it's a NASA mission that should be launched by 2030 and should observe in the near ultraviolet and the far UV. But let's focus only on the UV. That means the scattered dot. We can clearly see here that we have there is a huge difference depend to the where come from the UV. If the source come from the shock or the nucleosynthesis. But after 12 hours, we see that it's difficult to handle. Remember that we only have the data, we only have a data, no, the available data is after 15 hours. So until now, we don't know the real source of the blue light that we detected from the GW1708. So to determine that, we need to catch the early UV light. That's why Ultrasat is important for that, because it's a wide field of view. Okay, Ultrasat for ultraviolet transient astronomy satellite is an Israeli mission and planned to be launched by the NASA in 2027 and should observe the sky in the near UV. His field of view is about 204 square degrees. And the main mission will last 3 years, but can extend to 6. Okay, right now, let's dream a little bit. Let's imagine we are living in the future, specifically in 2027. And let's say that Ultrasat has been launched. So we can catch the first, the early UV and determine the nature of the bright blue. So it's not really easy because we have another problem. And the problem is the early UV emission fades within a few hours. So we need to react quickly. Secondly, a naive scheduling often with the exposure time. So our solution is to dynamically optimize the exposure time, focus on each field. Then we model the problem using a mixed integer linear programming. So solving with Cplex. Cplex is a IBM module. It's a commercial algorithm, but free for the student and for the researcher. At this figure, we have the linear programming. The line represents our objective function, and the field polygon is the system of the linear inequality constraint. Okay, we implement all these strategies in M4, including an absolute magnitude that we model as a Gaussian distribution. And also, we provide the gravitational wave sky map. Okay, we use also ILPix to read the pixel that's contained in the 90% of the total probability of the gravitational wave event. And the deeper color here, so the region with higher probability. And it's this region we need to efficiently cover. And inside of ILPix, we are able to use an adaptive grid. And for this adaptive grid, that means we can work at a different resolution. You can see it in the bottom figure. And this resolution is defined by the level. At the level 0, we have a 12 tiles. As the level increases, the map is divided into smaller pixels. And this helps us to manipulate the sky map, and also make sure that each pixel has the same, in one pixel, we have the same probability. Okay, let's talk about the observational constraint we implement in our scheduler. We have the field of rigor. So that means a ultrasat should point outside of the sun, the earth, and the moon. We have also the street time, and the street time is focused on the observation between the fields. We have the roles that concern the solar panels, and we can revisit the same field in order to increase the probability of detection. Also, what I will come back to the exposure time, and to be sure that we are in the same point. I talk about the dynamical optimization. That means for each field, we calculate a specific exposure time based on the local background, and also the zodiacal light, the galactic background, and also the Dastor extension. When we look at the figure on the left, we can summarize that in 2 points that show us how the exposure time changes across the sky, and also how the detection probability increases as we observe over the time. And we have the probability here in the blue. Okay, let's talk about what really happened in M4. Okay, what happened is we have our scheduler and we release a detection. What happened really is like we have the box color in the red that represents the field of the detector. And the green contour represents the 90% of the gravitational wave probability. And also, let me pause it to show clearly what happened. Okay, we have two types of outside of the field of rigor. That means we have the average one. The average one concerns the region that we cannot point during all the observation time. That's concerned for us here is from 0 to 24, so 1 day. And now the light blue is the instantaneous position. So here we see that we have the sun here and we have the moon here. So we cannot observe this part because we have the average out of field. But here we can observe after 4 hours. We can see here we have 0 to the 4 hours. We cannot observe, but we start to observe after 4 hours when the Earth start to go away. Okay, and that is what really happened with our scheduler. Okay, right now in M4, we supported 4 telescopes, a Ultrasat, UVEX, that is the space telescope, and we have the ground-based telescope like the ZTF and Rubin, that we have Rubin here. And here we can model a specific field of view depend to the telescope camera. Okay, we run our scheduler on all the simulated gravitational wave detection during the 05 and the 06. And we selected all the events with the detection probability more than 10%. On the bottom left figure, each point represents one simulated event. And on we have in the x-axis, the luminosity distance, and the y-axis, the credible region provided by the gravitational wave localization. The color dot represent the selected event. In contrast, the gray dot represent the event that were not selected. And the color of each dot represent here the detection probability, and the dot size encode the objective value of hours used by our scheduler. On the top, we have the distribution of the luminosity distance, and the right panel, we have the same distribution, but for the area. And we have the gray for the whole event. The blue one is the tag, the selected event, and the purple represented the detected event. Okay, we try to do some statistics in order to compare a Ultrasat and UVEX and evaluate their implication during the next observing scenario, principally the 04 and 06. And the number for the Ultrasat, the number of events that we are selected, so 45, and the detected, so 20. For the 06, we detected, we selected 60 and detected 27. And in contrast with the UVEX, we selected 29, but detected 12. And for the 06, 43 and detected 17. Okay. For the moment, for our contribution, we already have one paper published, focused on UVEX, and the second paper focused on Ultrasat will be soon on arXiv. And you can scan the QR code to join us. We also provide a process, a documentation to help students and maybe researchers who want to simulate observation plan that's cover M4 up and type I. And you don't need to be an expert. We show how to simulate gravitational waves from the detection to the release the observation plan.